Welcome again to another topic from this unit on electrons. Now, last time you learned about shell configuration, sublevel configuration, and orbital notation, as well as dot diagrams. And we're going to put that to use today in some practical applications of electron configuration. We're going to start off with quantum numbers, which are kind of like zip codes for electrons, how to determine whether an atom is in the ground state or the excited state, and whether these places electrons can be found are occupied or full. So let's go. Quantum numbers are useful for describing individual electrons. They're not describing necessarily the actual physical location of an electron, but their energy. And there are four different numbers that you're going to have from most general to most specific to indicate that position in terms of energy. Now, in a zip code, there are 5 digits, and you might have noticed that around where you live, the first 3 digits are very commonly the same. See, we have 125s up here, we have 109s down here, we have 105s over here. And so these numbers help to route mail so that you know exactly where they're going, and each postal system has its own unique zip code. Just like every electron has its own unique quantum number. So, like I said, there are 4 different ways you can express this. The principal quantum number, which is the first one you're going to write, is the principal energy number, principal energy level number. The sublevels for S, P, D, and F, this is the tricky bit. A lot of people will get this part of it wrong. S is assigned a quantum number of 0. P is 1, D is 2, F is 3. Now, it's only natural to want to say, I'm going to count from 1. S is 1, P is 2. But no, S is 0. All right, that if you're going to have a problem with quantum numbers, that's usually where it's going to be, forgetting that S is 0. Then P is 1, D is 2, and F is 3. The orbital depends on which orbital it's in. The center orbital is 0, and any orbital to either side will get positive or negative numbers. So if you go left, you get more negative, and if you go more right, you get more positive. So, for example, in a p sublevel, the center orbital is 0, the left is -1, the right is +1. In a D sublevel, the center is 0, and you become -1 and -2 going to the left, +1 and +2 going to the right. In the F sublevel, you notice that we have 0 in the center, going -1, 2, and 3 to the left, +1, 2, and 3 to the right. And finally, spin. The up arrow is +1/2, and the down arrow is -1/2. So if we have a third energy level electron in the p sublevel, and it's the orbital to the left of center down arrow, that will have a different quantum number than the first energy level, S sublevel, center orbital up arrow. Every electron will have its own unique 4-digit code. Here's how it works. So determine the quantum number of this electron. Well, first of all, it's in the second energy level. Therefore, the first quantum number is 2. It's in the p sublevel. Now remember, S is 0, so p is 1. It's not the center orbital, it's the orbital 1 to the right of center. And we go more positive as we go to the right. So that's +1. And it's the up arrow. And therefore, being the up arrow, the up spin gets a quantum number of +1/2. So the 4-digit code for that electron is 2, 1, +1, +1/2. The electron next to it would be 2, 1, +1, -1/2. Okay. What about this quantum number? Well, this time we're in the third energy level, so the first quantum number will be 3. We are in the D sublevel. Now remember, S is 0, P is 1, D is 2. It's not in the center orbital. It's 2 to the left of center, and you go negative as you move away from the center. So 2 orbitals to the left of center would be -2. And finally, it's the up arrow, and being the up spin will have a quantum number of +1/2. And that is the unique quantum number for that electron. Okay, what about that electron? Well, it's in the second energy level, so the first quantum number is 2. It's in the S sublevel, and the S sublevel has a quantum number of 0. It's the only orbital in the sublevel, so it's by default the center orbital. And therefore, 0 is the third quantum number. And it's the down arrow. And therefore, since it's downspin, -1/2 will be the fourth quantum number. So, stop me when you find the electron. First energy level, S orbital, S sublevel, center orbital, downspin. This is 100 +1/2. This is 100 -1/2. Okay. What about this one? Fourth energy level, P sublevel, center orbital, +1/2. Fourth energy level, P sublevel, center orbital, up arrow. That's the electron right there. Whee! There you go. All right. Now, excited versus ground. If you recall from a couple of videos ago, the ground state is where electrons occupy the lowest possible energy states. And if you give that electron energy from an outside energy source, the electron will rise to a higher energy level. But then very quickly, the electron will drop back to the ground state, releasing its energy in the form of light. So, how can we tell if an electron is in the ground state or in the excited state? Ground state or excited state, just by looking at its electron configuration. So, here is how it works. For principal energy levels, you can tell if it's in the ground state if the configuration matches what's on the periodic table, because on the periodic table, they're all ground state configurations. So, 2-7-2. Let's add those numbers up. 2 plus 7 is 9, plus 2 is 11. So now we look at the element. Sodium, element 11's, its ground state configuration is 2-8-1. Therefore, 2-7-2, since it does not match, that's in the excited state. Well, what's so excited about it? Well, normally there'd be 8 electrons in the second energy level. One of them has been excited to the third energy level. When it falls back down, it will give off light. 2, 8, 16, 2. Let's add these up. 2 plus 8 is 10, plus 16 is 26, plus 2 is 28. That's nickel. Nickel's configuration is, oh, would you look at that? 2, 8, 16, 2. It matches. Therefore, it's the ground state. Here's a third example. 2 plus 8 is 10, plus 2 is 12, plus 1 is 13. Element 13 is aluminum. Aluminum's ground state is 2-8-3. So one of these 3 third energy level electrons was booted up to the fourth energy level. Since it doesn't match, that's the excited state. So these are easy to get. Sublevel is slightly harder. Remember, electrons will fill up. 1s2 fills up first, then 2s2, then 2p6, then 3s2, then 3p6. Now, you might think 3d10 comes next, but remember we were talking about the diagonal rule last time? How there's overlapping between levels? Well, this is the first overlap. 4s2 fills up before 3d10 does. It's the only overlap you're going to have to worry about when you're doing these. And then 4p6 comes next. So 3p6, 4s2, 3d10, 4p6. So as long as one of them fills up before you move on to the next one, you're in good shape. So if it fills up in this order, then it's ground. If it doesn't, then it's excited. So 1s2, 1s2, 2s2, 2s2, 2p. Well, the last one doesn't have to fill up. Everything that came before it filled up before we got to it. Since it fills up in order, it's the ground state. 1s2, 1s2, 2s1. Well, if that's all we had, if we didn't have this, then it would be fine. But we can't start 2p until we fill up 2s. S requires 2 electrons to fill. We only have 1 electrons, and since they don't fill up, it's excited. This one actually is excited in 2 ways. 1s2, 2s2, 2p. Wait, it's supposed to go to 2p6 before you move on. So one of these electrons is missing. Not only that, but 4s is supposed to fill up before 3d does. So this one is doubly excited. Woo! It must have something really special coming. Maybe it's its birthday. Occupied versus full. So how many electrons does it take to occupy something? Well, how many people does it take to occupy a room? 1. If a room is empty, there's no one in it. If it's occupied, there's someone in it. Now, full means you've packed it to the point where no more can go in. So that's what we're going to be looking at, the distinguishing features of occupied versus full. So occupied, 1 is in there. Full means you can't put any more in. It's completely filled to capacity. Okay. So we're going to be looking at this once again at principal energy levels, sublevels, and orbitals. Let's start with principal energy levels. Our configuration is 2-5. If you recall, the first energy level can hold 2 electrons. The second can hold up to 8. The second isn't full, but it is occupied. Therefore, we have 2 occupied energy levels, but only one of them is full. One is full, and the second one is occupied, but not full. Okay, now we're going to do sublevels. We have 3 sublevels here, 1s, 2s, and 2p. Therefore, we have 3 occupied sublevels. S can hold up to 2, so these 2 S sublevels are full. P can hold up to 6. Right now, it's only holding 3. So this one is only occupied, not full. So we have 2 occupied and we have 3 occupied, but only 2 full. Finally, orbitals, occupied or full. Now remember, each small red box represents an orbital, and we have 5 boxes with arrows in them, which means we have 5 occupied orbitals. But orbitals take 2 electrons to fill, so only 2 of those orbitals are full. So 5 orbitals have electrons in them, so they're occupied, but only 2 of them are full. And those are some practical applications of electron configuration. And electrons that are alone in their orbitals, those are the unpaired electrons. Those are the ones that are involved in chemical bonding. More about that in the next unit. Until then, we are finished with this, so I am going to bid you adieu. Adieu. Parting is such sweet, sweet sorrow. And until next time, I'm going to have to say bye.